So next up, we're going to have Rini telling us about testing separation logic specifications.
Thank you. So this is joint work with Kayvan Memarian, Dhruv Makwana, Christopher Pulte, Neel Krishnaswami, and Peter Sewell. So our goal is to make system software more reliable. So when I say system software, I mean operating systems and hypervisors. And the majority of this software is written in C or C++. And the reason we care kind of extra about system software being reliable is because all other software runs on top of it. So a single bug can propagate upwards and cause big problems. And just to look ahead to later in the talk, we were able to apply this work to a fragment of some real-world hypervisor code. So stay tuned for that. So how can we make system software more reliable? One natural answer in this room and at this conference might be formal verification through writing functional specifications. So we take a classic or triple with a precondition and a postcondition, and we want some way of representing these specifications in our case, the C language. So you can represent this precondition in the C comment through a requires clause, and the postcondition through this ensures clause for some tiny C function. So let's say that we went along this path and we wanted full functional correctness verification. So step by step, we want to annotate our existing functions with these specs, prove correctness, which can take a really long time, and repeat for the rest of the code base. So as we all know, this is quite an all or nothing type of process, and sadly, we are still very much here on our pursuit of reliability of system software. And so we put a lot of time and money and blood and sweat and tears into this, but there's not really any reward as we go along this process. And bonus points if the code base that you're trying to verify is constantly evolving, like real-world software does, and you have to rewrite or maybe even throw away specs that you've spent weeks or months of your life writing. So what we really want is probably something that looks a bit more like this, some form of gradual assurance where we get rewards as we go along rather than having to wait until the entire thing is done. And so the idea here is to make these specifications testable at runtime. So you may be wondering, why should we test specifications when we can just prove correctness? Well, there's actually quite a few reasons we might want to do this. One is that testing fits the test debug cycle that real-world engineers are familiar with. So if they are more familiar with something, they are probably more likely to adopt it themselves. Another reason is that testing helps to guide the spec writing process itself. So you can check the specs at runtime as you go, which flags mistakes in the specs themselves quite quickly. Another reason, which is what I've been talking about until now, is it provides this on-ramp to full formal verification, so you get some kind of gradual assurance rather than a very all-or-nothing type of process. And a benefit of testing specifications in this way is that you get both testing and proof from the same specification, so you only have to annotate your program once and you get both kind of for free. So step by step, this starts out kind of similarly to the full functional correctness verification steps I was showing. So you start by annotating your existing code with functional specifications, but these can now be partial functional specifications. You don't need to write the pre and the post condition and the invariants and the assertions to get anything out. You can just write maybe just a precondition or maybe just an assertion and check this at runtime. And then we want to transform these specifications into runtime assertions in the source language. And I just want to point out that this idea is definitely not a new one. This dates back to at least the 1970s with executable spec languages for Ada and Euclid. But we would argue that this is kind of underappreciated in the field of verification as a whole. So now let's get back to the task at hand, testing specifications for C, for systems code. So looking at this tiny example from before, what we want is we want this precondition to execute at runtime before the function body, and we want the postcondition to be translated in this way such that we can execute it before any point of return in the function. So the closest related work to this for testing specifications in C is EACSL. So this is an executable fragment of Frame-C specification language, and it uses first-order logic. So Frame-C has been, for a formal methods tool, that has really been applied quite well in industry. But one of the problems with this approach is that it uses first-order logic, which makes it hard to capture the complex ownership patterns that are present in virtually all C programs. So this is where we come to the work for this paper, Fulminate, which is a tool for testing CN separation logic specifications in C. And so because we use separation logic, we're able to capture the complex ownership patterns of imperative programs. So first, we want to annotate our C code with these partial separation logic specs. For this work, we have built on top of the CN verification tool. So CN is a proof tool for C. It's a separation logic refinement type system with an SMT solver backend. And it aims to provide kind of predictable verification, so you can get some yes-no result of whether your program can be proved or not. And it's built on top of Cerberus, which is a well-validated semantics for a large fragment of ISO-C. So the CN specification language was designed to be intentionally inexpressive, and the language has input and output variables rather than unbounded quantification. And this was designed to be within a decidable fragment of SMT, and it turns out that this decision serendipitously was very good for the executability of specs. And when I say good, I mean it's what actually makes this possible. So on the bottom left, we have a classic separation logic points to. There's some value such that some heap address P points to V. And on the bottom right, we have the CN representation of this. So you say take V equals owned of P, where P is some heap address, and we bind the value stored in that pointer into the variable V. So now let's look at a classic linked list example in CN. So this is a classic separation logic linked list predicate. So we say that for some heap address P and some mathematical list X's, either the pointer P is null and the mathematical list X's is empty, or we're in the interesting case where the pointer P points to some head value and some other pointer Q, and recursively the int list predicate holds for Q and some mathematical list tail, and X's is head and tail concatenated together. So classic example. So now let's look at this in CN. So we have this predicate which returns something of the type integer list. So it returns the mathematical list. And we have if statements instead of if and else statements instead of disjunction. And we say if P is null, return the empty mathematical list. And otherwise, we use this take node equals owned of P. So in the angle brackets, we just have this optional C-type annotation, which is the C-type of node. And then we recursively call int list, we store the mathematical list, and then we return these concatenated together in this CN data type. So once we've annotated our C programs, we want to transform these specs into C runtime assertions. So we start with a C program with CN annotations. We generate some ASTs of both the C program and the CN specs. We then perform the source-to-source translation. So this becomes an internal representation, a C-like internal representation of the translated CN specs. And then this turns into the C program with inserted runtime checks, so we pretty print and inject back into the source program. So now just going back to that int list example, I just want to talk a bit about how the dynamic ownership checking works within this tool, Fulminate. So let's say we have a simple linked list, which is the mathematical list 315. And now let's assume that we have some precondition in CN. So we say requires for the precondition, take L1 equals int list of P1, which is the pointer to this linked list. So first we check if the pointer is null, it's not. We move through to the take node equals owned of P. And this is where we have a global ownership ghost state that keeps track of what is owned and what isn't at any point in the program dynamically. So at this point, we color P1 as owned in this state. And we know that the struct node that is returned from this owned predicate is like this. And then we recursively call int list. We continue. We know that node.next is this pointer p2. Let's continue. P is still not null. We get to owned again. We again color the go state. And this continues similarly until we reach the end of the linked list. So we color p3 as well. So now we're in the interesting case. We've reached the end of the list. So P is finally null. So we return the mathematical list, and you can imagine that we construct this as we go along, back up the call stack to give us something that looks like this. And we've successfully colored the go state to say what is owned and what isn't. And if we just imagine that this was a post condition instead, so in the case of the post condition, when you reach the dynamic ownership function, it sort of uncolors the state to say we don't own this anymore. So I did simplify this a bit. The two simplifications that I mentioned, so one is that we don't actually have a flag to say we own it or we don't. We actually record the function stack depth. And also, instead of just coloring the pointer itself, we color for the number of bytes. So we track ownership per byte for the size of the C type of the value at that heap address. And because of time constraints, I'm not going to go into this too much, but our paper includes a formalization and also a proof that the runtime ownership go state correctly captures explicit resource passing. So now let's talk about the applications of this work. So this is what I was alluding to earlier. So PKVM is a hypervisor that's in development at Google to protect the Android Linux kernel. So we applied Fulminate, this tool, to a fragment of this called the buddy allocator. So this was annotated with CN specs as part of the original CN paper 2 years ago. And so just for a sense of the scale, it's about just over 300 lines of C and about 700 lines of CN specs. And it took about 30 seconds to run Fulminate, generate the tests, generate the assertions, compile, and run the binary. The majority of this is the generation time. And this is not the fastest in the world, but it's also good enough for our purposes for small critical examples of systems code. Another application of this work is Verse. So Verse is a DARPA project that is designed with the aim of making formal methods accessible to non-experts. And this is a collaboration across academia and industry, multiple universities, and industrial partners. And as part of this project, we're working with human-computer interaction experts, specifically at UPenn, who will hopefully be able to conduct realistic user studies on how people find using CN and Fulminate. And a work-in-progress part of this plan is to apply CN proof and testing to a large-scale hypervisor called the OpenSat, which is being written from scratch as part of this project. So to summarize, Fulminate transforms CN separation logic specs into C runtime assertions. CN's restricted syntax is what makes executing these separation logic specs possible. And this kind of takeaway from this talk that's more of a general point is that we think that testing specifications is arguably a bit underappreciated in the verification community, and we would welcome more work towards bridging the gap between these communities. Thank you.
Questions from the audience?
So you generate one concrete test really per function that you have specified in CN, right?
So we generate whatever you write a specification for, that gets translated into some assertion.
One test per, do you generate many tests or?
Do you mean concrete test cases?
Yes, the test case, what's the root, what's the main function of that test case?
So that's the thing. So this work is not, I think maybe this is a common misconception about this work. So it's not property-based testing or generating any concrete states. So for our purposes, what we've been doing is maybe writing some main functions by hand to drive these assertions at runtime in C. But this tool is just doing the source-to-source translation of this functional assertion language into C, basically.
So then the developers write their own concrete tests and it adds asserts in the function calls.
Yes, exactly, yeah.
Have you, sorry, second question. Have you tried running some of those tests with like CBMC or GNC or CPA checker or some of that? Is it resilient to that?
Sorry, say again?
Is it resilient to that, like, because you have a lot of ghost state?
So we haven't tried this yet. This is definitely on our agenda now that the tool is in more of a state that we can do this. And yeah, in terms of whether it's resilient, so currently the allocator for the ghost state, as you were saying, it's very basic and it runs out of space kind of, after some certain size. So we definitely want to implement some kind of garbage collector and try and actually check that that's going through with like industry tools, like a fuzzer or something, like AFL maybe.
Hi, thanks for the talk. That sounds cool. I was wondering, so do you support concurrency? And if not, do you think it would be hard to support concurrency? Because it seems like there could be race conditions on this ghost state you're maintaining, so you probably have to do something.
Yes, this is a good point. So concurrency is also on our kind of near-term path. So now that we have it working in a sequential setting, especially in these kinds of systems code like PKVM, where we actually have to account for this. In terms of whether it would be hard, I think it depends on the sophistication of the concurrency. So we could start by adding some basic locks and trying that. It would also have to work for the CN proof. So anything that gets added to the language needs to work for proof and testing. So we're still in the process of working out how we want to do this.
If I may, do you support a question? Do you support magic wands? And if not, have you thought about what that would entail or look like?
I don't think we use magic wands right now. I haven't really thought about what that would look like at runtime, to be honest, but we can talk about it later if you want.
Okay, yeah, happy to. Thanks.
Still have a question?
Hey, so this reminds me of tools like Volgrind or address sanitizers, which would check ownership for you without you having to write any specs. And so I guess this goes beyond that. And also, did you find any bugs in PKVM or others?
We didn't. I'll start with the second question and then go back to the first. So we didn't. So we've only applied this to a fragment of PKVM. This is, another thing. Next steps is trying to scale this up to the rest of PKVM, which would involve writing these CN specs and then running Fulminate on it. In terms of how it's different. So you need these explicit annotations to keep track of the ownership throughout. Maybe we can discuss this later if that's okay.
We do the laptop switch now. We can take another question or two over here.
Hi, so I was wondering how complex are your specifications? Like, what is the most complex specification you have?
Sorry.
You don't support the one operator.
Okay. Sorry, could you repeat that?
Yeah. I was wondering how complex are your specifications? Like, we saw the example of the list, but what is the most complex specification you support?
Maybe I just go back a few slides. Oh, yes, that's true. Good point. I'll just read the slide I went back to. So the example I showed was kind of intentionally simple. So another form of evaluation for this paper was also that we applied Fulminate to these tutorial examples, which were kind of borrowed from software foundations and various other places. So that's one type of example where the specs are relatively simple. For something like PKVM, the specs are going to be much more complicated. Like I said, it's 700 lines of CN spec for 320 lines of C code. So that includes preconditions, postconditions, loop invariants, inline assertions, whatever you would need for the proof to go through. But also, as I mentioned, for the purpose of testing specifically, you don't need to write the full spec, right? So your spec is kind of as complex as you want it to be in this incremental setting.
Okay, thank you again.